We're now going to turn our attention to multidimensional gradient descent. In many ways, this is very similar to the one-dimensional gradient descent that we used in the previous lecture, but there are some important differences. One of those important differences is choosing our mu, our step factor, now becomes a little bit more complicated. We'll start with our weight update equation on the left and the expression that we developed for the expected squared error. Finding the gradient of the expected squared error yields this simple expression: 2 times the covariance matrix times our delta weight vector. Now the delta vector, as defined previously, and as you may recall, is just equal to our current weight vector, in this case, minus the optimal weight vector. Combining these expressions gives us the weight update shown. Now recall that we have another expression for our optimal W, which is Ry inverse times r dy. And so let's shove that in there, and simultaneously we're going to factor out and combine our wi's. So as of now, this looks just like what we saw in the 1D case. The only difference is that Ry is a matrix and Rdy is a vector, and so are our respective weight vectors are Wi and Wi plus 1. So we're going to do a similar analysis to see how this behaves. That is, we are going to express everything in terms of our deltas now with by subtracting W opt from both sides, and we'll get an expression similar to what we had in our last lecture. So now we can write this in terms of our delta W's. And now, based on this, a little bit of simple deduction, or induction rather, tells us that we can express our weights as a power relationship with respect to our initial condition, our initial guess. Okay, so this is very similar to what we had before, but now I minus mu Ry is a matrix, not a constant. And so determining the behavior here is going to require a little bit more work. But before we do that, let's go back and see what's going on logically as we do each of these steps, or maybe in a graphical manner. We can think of our initial, I'm going to just draw these in 2D as best I can, which is hard enough, I guess. We can think of our initial system as having contours around some optimal point. So in this case, if this is our optimal weight W0, optimal weight of W1, so that's our Wiener solution, then the error curves are going to grow around that point. Like so. So this could be viewed as a contour plot. Like so. So as we have some initial error point, or some initial guess rather, maybe our initial guess is here. I guess our notation is failing a little bit at this point. So I'm going to call this our initial guess, and we'll do it this way. Opt 0, and this will be W opt 1. So our initial guess is going to be here, and we will follow the gradient, hopefully, to get to the solution. So the gradient will be downhill down to our solution there. We want to find out how this works, so the first thing we do is we switch to using our deltas instead of just the straight weights that we had before, and that gives us something that is now centered on the origin. So here's an example of such a centered plot. Later, we're going to show that we can do analysis that better shows how this behaves if we then rotate this plot so that the major and minor axes align with the dimensions of W. But this is as far as we'll go for right now. I would, however, like to take a few minutes and talk a little bit more about these contours, the curves of constant error. They're given, they're ellipses, and they're given by the expression that W transpose Ry delta W is equal to a constant. So here are two examples. The first is a relatively simple one. We're going to let Ry be the matrix, the identity matrix, and we'll be concerned with the eigenvalues, which are going to determine the shape of our ellipses. So the eigenvalues of Ry in this case are simply lambda 1 equal lambda 2 or equal to 1. So in this particular case, our curves of constant error are just given by delta W 0 squared plus delta W1, so those are the first and second elements of our vector delta W, are just equal to a constant. And so we know what this is going to look like. It will simply be circles. Each curve is defined by choosing a different value for C. So in this next example, we have something that has off-diagonal elements in a 2x2 case. And we get something that's more, well, that is elliptical instead of circular. In this case, the eigenvalues are given by 1 plus alpha and 1 minus alpha. This is something you should check on your own to verify. And it's these eigenvalues that determine the shape of the ellipses, or the relative dimensions of the major and minor axes of our ellipse. The ellipse itself, the curves, the equal error curves, are described by a function similar to what we had before, but now we're going to have some cross terms in there as well. So we have delta 0 squared plus 2 alpha delta 1 delta W1 delta W0 plus delta W1 quantity squared are now equal to a constant. I've included some MATLAB code for creating these error contours. A few things to note in looking at these. One, we use code for plotting a parametric circle where we scan through the angle from minus pi to pi in small steps, calculate the points with the sine and cosine, and then plot those points against each other. That code is shown in the upper right. And then down here in the lower left, we're showing an example for alpha is equal to 0.9. We find the eigenvalues, and we do the same type of a plot, except now in the direction we incorporate two other things. One is the eigenvector, and the other is the eigenvalue. So the eigenvector determines the direction in which the our ellipse is oriented, and the eigenvalue determines how it's scaled in that direction. Notice that the eigenvalue is divided into the cosine. I've generated several plots here at different several error contours with effectively different constants, as you can see out front. And so now you have all the tools you need to generate your own error contours. But the most important thing is that in the direction of the larger eigenvalue, let me just write this here. This is direction of the larger eigenvalue. The plot is narrower, our ellipse is narrower. And in the direction of the smaller eigenvalue, the plot is relatively stretched out.